Our next speaker is Kent Hoofaker. Mr. Hoofaker has been with Battelle for 36 years conducting research in the areas of aerosol science with an emphasis on applications to CBRN, defense, and homeland security.
Thank you. I'd like to recognize my colleagues, co-authors on this paper, Mike Wusso, Dave Durden, Ryan James, and our technical representative from EPA, Tim Bowe. We were all part of this field demonstration that I will talk about today. I was present. Mike and Dave are the subject matter experts on this work with regards to the unoccupied aerial systems and the associated imagery. All of my colleagues are out doing something else, so I'm pinch hitting for them today. So the objective of the project was to see if the objective of the project was to see if we could take UAS technology, both the drone and the imaging, and apply that to evaluate whether or not it's useful to render images, accurate images, to estimate the volumes of objects, say in a debris field. The idea here was to compare the volume estimates of objects in a debris field with the two UAS systems to ground measurement techniques, sort of ground truth, the measuring tape, and the global navigation satellite system. Ultimately, do the UAS systems provide an accurate estimate of volume compared to those ground measurement approaches? And whether or not they offer some safer and more expedient methods of obtaining the volume estimates. I will say that this part of the field demonstration was part of a larger research effort in which is not discussed here. The two UAS systems, structure from motion. This is effectively taking many photographs from the air, stitching them together to produce ultimately what's called a point cloud, a rendering of that object from many different angles. And the idea here, again, is to build that object, render it based on, as you'll see later, maybe thousands of images of a selected object. The other UAS system was LiDAR. And effectively what's going on here is there's a light source pulse emitted that directs to the ground in this application. And there's a reflection of that signal back, and it's collected by a sensor. And through processing, again, suffice it to say, you can generate a point cloud with such a system and give you the surface features of object in view. There was a range of objects that were interrogated, investigated in this field demonstration. Here are some of the complex objects. Starting at the bottom, there was maybe organized piles of stacked lumber, stacked pipe, or maybe there was a shed that was available. You got into more complex objects in the sense of more random, maybe a pile of wood debris. And then lastly, large random stacks of woods, such as if you were to bulldoze debris together into central location, very irregular shape, very complex shape, as well as a down tree. And there'll be more images of this throughout. In the picture to the left is the large wood pile object that was imaged and rendered. There was a man-made, if you will, set of objects that were placed out there. There was a tall and a short stack of pallets, purposely stacked and placed as shown here, such that well-defined geometry, would lend itself to very accurate hand measurements with a measurement tape to estimate a volume. For frame of reference, the tall stack is maybe on the order of about 4 feet, the short stack about 2 feet. And there may be like 3 foot by 3 foot square on the short stack and maybe 3 by 4 foot on the tall stack. The idea here is again, you could measure those accurately with your hand measurement technique with a measurement tape, but the other UAS methods would also have a well-defined object, because if you couldn't establish a good volume estimate correlation here, then kind of why bother with the rest of the effort. So this was kind of baselining with this ground truth reference object. The LiDAR system is shown here. The team, Mike and Dave, down selected with different criteria, cost, endurance, how long could it fly, remain airborne, payload capacity, and also wanting to have a US system. So that limited the selection. But the one of the points with the system was they're disparate pieces. The drone from the LiDAR were not necessarily meant to work together. So Mike and his team has put significant effort into having the drone and the LiDAR camera sensor function as a system. The structure from motion, however, that drone and camera system was built and designed to function as one, so that integrating of disparate parts was not required. The features, some of the key elements of the system are noted to the left. The pad here is a reference for geolocating. There's GPS in the system here in the camera. However, it's not a high resolution. So these reference markers were placed throughout the area being interrogated, being surveyed. And then in the post-processing, you could find these reference points and then accurately locate the objects in the surveyed area. Suffice it to say that both aerial systems required mission planning. What's your flight pattern, all pre-programmed into the UAV, and your elevation, your path width, the number of paths. You have to have a lot of overlap. And again, suffice it to say that that was all pre-planned and load programmed into the UAVs for their operation. Another slide here on mission planning. Take note here that covering about an acre per minute on the imaging. And one thing I failed to say earlier was the application for these UASs was kind of thinking of a scale of operation where maybe you're trying to survey hundreds of acres, sort of an area, just for frame of reference, 1 square mile, 640 acres. So that was kind of the application. It's not so large that you need satellite imagery. But we were covering, with this flight plan, about an acre every minute, give or take. This is the field team, all 4/5 of us. Ryan James took the photograph here, but you can get a sense of scale of the UAV compared to us standing around it. It was a very clear, there were light winds for sure. They were picking up. We did the survey in the morning, were fairly calm winds, relatively speaking, but a very clear day, very conducive for flight operations. Getting into some of the ground data collection with the hand tape. On the left, you see Dave with a tape measure. This is the large wood pile. You can just see how irregularly shaped it is. It's highly subjective, right? You know, where do you want to pick to make a height measurement? And quite honestly, over this pile of debris, we took several height measurements because it's not uniform. It's not a well-defined geometry. But then you can also see on the right some of the more, believe it or not, organized piles of debris. Again, with hand measurements, again, very subjective. Where's the outer perimeter of that pile of wood that you're surveying? And where do you make a height measurement? So a lot of judgment involved in the hand tape measurements. Ground data collection with the GNSS rover. So you have a transmitter at the top of that pole, and you're moving that pole around different locations on the pile, and that you capture a signal, you get an elevation. So the idea here is you're going around the perimeter to kind of get the projected area, and then different heights to get kind of the envelope of that object. Very time consuming. But on the right, you see sort of a random pile of wood. So here's where you can see where the hand measurements are maybe not always a safe or secure operation. Mike is standing and walking around on that pile. It's unstable. It's difficult to maneuver. And characterizing and making 10 12 measurements on this pile is 20 30 minutes of navigating around that, but you can begin to see as a practice you probably don't want to be climbing around debris such as this. So there were 2 areas surveyed when we were out there. The team of the 5 of us, we worked this west area. And again, to give you some framework here, 22 acres imaged, surveyed, in about 30 minutes for each of the flights by the 2 UAS technologies. But in that 30 minutes, we have all objects scanned and then data captured. So you can go back and pick any structure, any object you want to process to estimate the volume. Conversely, with the hand measurements, you're having to pick very discrete objects, and you may not capture all that are of interest, or it's possible you just have to invest a lot of time. And in 30 minutes, you got all objects surveyed. To make the hand measurements, those were hours and hours spent in the morning just to get very specific objects. The second area surveyed, not by the entire team, but just Mike and Dave, was done the second day. And the idea here is they're just more handmade objects, more debris throughout, not necessarily naturally occurring. And the idea here is that again, about an acre a minute covered. And it's not shown here, but you can get some high resolution imagery off of these the SFM. So no matter what technique used, there's some post-processing, right? So even the hand measurements, you're taking a length, a width, or multiple lengths and widths and heights to try to fit some sort of basic geometry and come up with a volume estimate. That large wood pile, we said, well, that's kind of the top half of an egg shape if you cut it lengthwise. But then with the other 3 techniques, GNSS and the 2 UAS methods, the data set that's collected, there's post-processing involved with software, ultimately to prepare these digital elevation models, DEMs. By no means am I going to try to go through this flow diagram, but the point of this slide is, again, multiple steps to go through with post-processing software to ultimately provide inputs to the Metashape software. And it's the Metashape software that created the DEMs the digital elevation models that allowed the estimation of the volume. So again, speed on the front end, but absolutely post-processing effort on the back end. So results. We talked about the pallet stacks being sort of the ground truth. A well-defined geometry lend themselves to making accurate measurements by hand. And in this plot, the volume estimates made by SFM and LiDAR are compared relative to the hand measurements. And you see for the large pallet stack that, well, for all of these, plus or minus 10% with a few outside of that. So very good agreement as expected for a well-defined geometry. And you can see the magnitude here of these objects, large or the tall stack, 1.5 cubic meters, the small stack or the short stack, maybe 0.7 cubic meters, not large objects. And so you can begin to see even small objects you can resolve pretty well and get good agreement with your hand measurements. Just again, another picture of the tall pallet stack. And again, another point to be made and be discussed throughout is the agreement between the SFM and the LiDAR estimates. They consistently perform very well in giving very comparable volume estimates. And again, no surprise, very good agreement with the hand measurements. So some of the output from the software, the DEMs, the renderings of those structures, of those objects are shown here. I think the difference in size is just sort of the zoom that was taken for these images for the presentation. I don't think one is imaging appears smaller than the other. I think it's just the zoom. But you definitely see the outline of the feature of the object. From the profile, you get very comparable images from the LiDAR to the SFM and even the GNSS measurements. Keep in mind the GNSS measurements, again, are based on your placement of that transmitter. So if you're not working around the perimeter, your profile might look wildly different than what's shown here. The short stack is shown here. And one thing to pay attention on that short stack on the picture on the right is you see there's like 3 main slats, and then there's like low spots between these. Here's your 3 slats. Then there's like little valleys, if you will, here. And you'll see in the next slide here that the UAS imagery is able to pick that up. Again, we got pretty good agreement here between the 2 volume estimates. But again, you're resolving these peaks and valleys are in the order of 4 or 5 inches, right? And you're able to resolve that. You're able to see in the profiles that the imagery is that's taking into account those shape differentials. But overall, as you would expect, the profiles are very comparable. The volumes estimated are very comparable. Moving on to more complex objects. No longer trying to compare to the hand measurements because the objects are such that the hand measurements aren't considered ground truth. And here we're comparing SFM to LiDAR. And so 4 of those 5 complex objects, you see, again, very good agreement. BFT, the big fallen tree, not such good agreement, but we'll talk about that in a slide or two. Even so, not comparing directly to the hand measurements, they're still within a factor of 2, the volume estimates made by hand versus the SFM or the LiDAR. So looking at this complex object of the large wood pile, again, a lot of climbing around it. It took us 30 to 40 minutes to get the GNSS measurements to get the volumes here. Again, factor of 2 and the magnitude of the measured volume. And overall, I think pretty good agreement, right? It's it's to be expected considering the relative complexity of that shape and topography of that shape. And again, you really don't want to be climbing around that. We limited how many points we could make with the GNSS. Profiles in the DEM are very comparable and similar as expected because the volumes of LiDAR and SFM are also very, very comparable. Here's the big fallen tree. So the challenge with this is there's a lot of void volume, a lot of space, right? So we didn't even attempt to make measurements with the GNSS, with the hand measurements, with the tape. We just considered the trunk of the tree. But SFM and LiDAR, they're capturing more the envelope, if you will, of that tree canopy, and hence make much higher, much larger volume estimates. And, you know, perhaps if you know that you have objects like this in your debris field, maybe you consider whether you apply a correction factor for a void volume like that, but something to consider. Profiles as shown here, very comparable between LiDAR and SFM, as well as the DEM images. Some pictures from the east area that was done by Mike and Dave after the rest of us left. And again, I mentioned it earlier, this is imagery from the east side, if you will, but you get very high resolution. It's very clear to make out the tires in that pile and the other debris to identify. So in conclusion, the UAS methods were found to be satisfactory for all measurement types. I realize satisfactory is a subjective term, but I think when you look at the comparisons of the volume estimates made, when you get a well-defined object, very good with the ground truth, the hand measurements. The SFM and the LiDAR consistently gave very comparable volume estimates of even piles of debris that were irregularly shaped, have very complex surface structure. And again, with the UAS, with one survey, you have all the data. You don't have to go back out. You can post-process, and you get thousands of data points versus 10, if you will, as an example, very relatively few for the GNS. And if you wanted more, you'd have to go back out and survey. I think bottom line take home was for these expedited needs in medium coverage areas, medium being, think hundreds of acres, the UAS can be accurate and valuable tools for post-event volumetric mapping, opening up response capability, especially where ground access is unsafe or limited. Advantages, disadvantages. Yeah, you got to have the right weather, appropriate conditions to fly. Considering time, I'm going to move on here. There's definitely initial capital investment and investment on training and personnel. So the UAS systems, they're not cheap. There's initial capital cost. You got to have trained personnel. There's no way around it, both for flying the missions and then the post-processing, the data reduction and analysis. Got to have the right weather conditions to fly. Troubleshooting, it's a piece of sophisticated electronic equipment in the field. You're no doubt going to have to troubleshoot at times. If your tape measure breaks, you could just get another one and you're back in business, but maybe not so much with these. I think with that, time's up. I'll conclude. Thank you.
We have time for maybe one quick question. All right, let's thank you. Sorry. All right.
Hi, this is Tara Haxton from US EPA. I just had a question related to like the cost benefit. Have you done that kind of analysis yet? A cost benefit analysis, kind of like, obviously it takes less time than doing it manually, but how about like an operator to fly the drone itself, like the equipment itself?
To my knowledge, they haven't, but Tim? No, not yet. Okay.
All right, thank you.